vaccine against HIV. So again, this is the funny thing about, or not funny, haha, but this is the interesting thing about HIV, is that this reverse transcriptase is also very error prone. So let's take things like the varicella zoster virus, the chickenpox virus, and again, back there, or actually it's kind of funny. Your parents, ask them how they got immunity against the varicella zoster virus or chickenpox. They might tell you that they used to have the neighborhood, someone in their elementary school class got infected. They would bring them over so that they got infected and that they would have built up immunity. I think everyone born around the late 90s actually had a, now you have a vaccine, you didn't have to go through the actual infection with chickenpox. So the mutation rate of that chickenpox virus is around like one mutation versus, and so out of every third, if you're making a copy of the chickenpox virus, for every 38 million nucleobases, maybe one mutation in during that process. Now, HIV mutation, what happens here? So basically, HIV mutates every 250 nucleobases. So pretty much every time reverse transcriptase does its job. HIV mutates at, again, 1,500 or 150,000 times the rate of varicella zoster virus. So every time HIV copies itself, it makes a mutation. So every time you make a mutation, what does that do? Again, remember you go from DNA to RNA to protein. So the proteins are always changing slightly. You have HIV changing slightly every time it replicates. So it's a moving target. This is why it's really hard to create a vaccine against HIV. Every time it replicates, every time it pretty much mutates. So this moves the goalpost. So even if you generate a vaccine against a HIV strain, maybe a few generations on, it might not recognize that same protein because it's mutated a lot. So this is why HIV vaccines are really hard to generate. So can HIV be cured? So right now, this is why patients with HIV and AIDS are living longer. So we do have therapies, but again, has anybody ever been cured of HIV? So there have been a few, but you can count them on a hand. So this is the Berlin patient. So this is what happened here. So what he had is actually not only did he have HIV, but he also had leukemia. So what they did is treat the leukemia by giving him chemotherapy. So chemotherapy killed the leukemia, but also got rid of all his bone marrow and his hematopoietic stem cells. Remember, hematopoietic stem cells, they are responsible for generating all the blood cells in your body, red blood cells, platelets, and leukocytes, which include your CD4 cells, CD8 cells, and T helper cells, B cells, plasma cells. So they obliterated his immune system and transplanted a healthy donor's immune system. And this is the interesting thing. Some people won the genetic lottery, and one of the receptors that HIV binds to, the CCR5 receptor, is mutated where HIV can't grab onto it. So they took someone who was resistant to HIV, took their bone marrow, transplanted it into him, and then he was resistant to HIV. So he's been off antiretroviral drugs, he hasn't had any other therapies, and he has no presence of HIV at all. And the great thing is that it's been replicated twice. Second, I think the second has been confirmed. And third, I think they're still investigating. So now they have the London patient, the Dusseldorf patient. So yeah, it's amazing. But the thing is this feasible? No, you have to give chemotherapy to these people. Can we give bone marrow transplants to all HIV patients or patients with HIV? Again, just getting a bone marrow transplant is hard enough to begin with, but it does show that HIV can be cured, but this is not feasible to scale up in the long term. All right, so what will be the cure for SARS-CoV-2, the novel coronavirus that's causing COVID-19? So that's the difference. Often you hear it being used interchangeably. I think I've slipped up and used it interchangeably. HIV is the virus, AIDS is the disease. SARS-CoV-2 is the virus, COVID-19 is the disease. So this is the life cycle of the original SARS, and it behaves very we think it behaves very similarly in SARS-CoV-2. So we have the SARS virus binding to these ACE2 receptors and integrating itself into the cell. But this is a thing. Instead of having a DNA genome, it has an RNA genome. And then what's able to do is use this RNA to create its own proteins and also create multiple copies of its own genome as well. Eventually, hijacks the internal machinery of the cell to make more viral proteins and more viral genome, and then buds off to the rest of the cells and infect the rest of the body. So you might hear like, oh, chloroquine is a new thing, and so the things like, oh, chloroquine or Avigan and so drug development, can we develop a new antiviral drug? Well, the thing is that all the drugs that are on the market, every new drug, actually spend on average like 10 to 15 years in development. So what they're trying to do now is take drugs that already have passed this. So these like take drugs that we are prescribed, and they're just trying to screen it and see, okay, does this actually work against like we have drugs that we know are safe and won't kill a patient. Let's take every single drug we know, throw it against SARS-CoV-2 and see if it inhibits it. So the thing is that that takes time, that takes money, that takes effort. And the other thing is that they can't test it, and sometimes they're trying to bypass it altogether and just test it as last ditch resort to help these patients with COVID-19. But again, this is why it takes time to. So are we going to have a new drug against that's specific for SARS-CoV-2? Not for a long time, because again, this process takes years. So SARS-CoV-2 structures. So what would be the best strategy? This is why there's a worldwide effort to find a vaccine. Because again, vaccine, you want to train our immune systems before you encounter the actual SARS-CoV-2 virus. All right, so what I think would be this thing. So think about these spike glycoproteins. These are the ones that are binding to these angiotensin converting enzyme 2 receptor. And angiotensin converting enzyme, remember that from our blood lecture? So remember angiotensinogen to angiotensin 1 to angiotensin 2. This is the one angiotensin converting enzyme. That ACE is the same one that converts angiotensin 1 to angiotensin 2. Now this is a receptor for that enzyme. So again, that's why high blood pressure is linked to increased risk of complications from COVID, right? Because it's binding to that receptor. So if I was creating a vaccine, what would I target? So I would actually target this spike. Why? Because this is the one that's actually growing, glomming onto this ACE receptor right here, right? So if I give a vaccine that's trained to bind to this spike receptor, it's going to block these spike proteins from binding to this receptor, thereby preventing these cells that have the receptor from being infected. So if you're able to opsonize, create antibodies against the spike protein, this prevents SARS-CoV-2 from binding to the receptor, hopefully preventing all the complications from COVID-19.